All right. So good morning, good afternoon, everybody. Today, yes, at a time. Yeah, it was brutal last night. Today, what I want to do is I want to talk about correlation and regression, which will be our final topic before our first exam. So let me talk about that before we get into the lecture. So if you look at our online classroom, under our course syllabus, you look that we have our first exam next week, next Tuesday, actually. So I'm still working out exactly the format of the exam because, this is a remote learning course. So I'm going to have more information on that on Thursday. But we will all take it during class time. I'll talk about it in a second, Pamela. We'll all take it in class time on Tuesday. I originally had asked that people put on their Zoom camera for the lecture. I would really appreciate it if you just did that for a second, but I understand if you can't or you feel uncomfortable with it. I understand that. I get that. It was a little harsh on that. So, so first off, to get ready for the exam, I posted your next homework. So if you click in class on the homeworks tab, you'll see here's your next homework. So this is a much, much longer homework than the first one, okay? So I think it's 7 questions. The only question you won't be able to do, actually I'm not sure how far we'll get exactly, but is question number 6. Question number 6, I'm not gonna get far enough really to be able to show you exactly today how to find the least squares regression line with your calculator, so we'll get to that on Thursday. But I highly encourage you to take this homework and start it this week, and then come to class on Thursday with any questions about it. I've also, if you look under course content, I opened up the tab for next week. I posted the exam I gave last spring. Okay, so this last spring was an in-person class. So I'm going to, it's going to be a little bit different this semester, but you can see roughly the type of questions that I'm likely to ask. Okay, the format of the exam, what'll happen there'll be a tab here called exams. And on exam day, the exam will get posted here. And to answer the question in the form, it'll be a mix of questions. Some of it will be multiple choice. Some of it will be you have to write stuff in. Some of it will be like you have to put the answer in. But I will come to class 10 minutes early and I'll stay, 20, 15 minutes after class, in case you run over or you have any formatting questions with it on next Tuesday. All right. Does that answer some of the questions about the exam? Okay. I promise you, if the best way to get ready for the exam is to look over the first homework. If you click on homeworks tabs, I posted the solutions for the first homework. I'm not going to post the solutions for this, okay, because these are very much akin to what your exam questions are going to look like. So if you struggle with these, you should definitely either ask me questions on Thursday or come to my office hours next Tuesday before the exam, all right? But give this a shot, okay? All right. Would it be like when we wrote on a graph? No, so all the questions will be posted online, okay? Because it's time constrained, I don't want to have to worry about people printing stuff out and scanning it in that time constraint. It will be all in Blackboard. All right, you actually won't have to do any graphs in Blackboard, so that helps a little bit. Okay. Yeah, no problem. Any other questions? You will have the entire class time to do it. Yep, all 2 hours. Yeah. All right. I write the exams just so we're clear. I write the exams so that someone who has like a really good understanding of the material can just like boom, 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 45 minutes to an hour to do the exam. But I give you the 2 hours, you know, because you've never maybe seen the problem. I mean, you should have seen the problems before. There are homework questions or I've covered them in class basically. But if you have struggle kind of remembering with it, I give the full 2 hours. Okay. Yep. All right. How many people have their graphing calculator with them today? Okay. All right, so today we're going to mess around with our graphing calculator a lot. Okay, we're going to change some default settings, the whole deal. And especially on Thursday, we're going to use it a lot too. So today what I'm going to have loaded up is the TI-84 emulator, but oops. If you have a TI-83, it is the exact same options, okay? So there's not much difference in it, okay? If you have the TI-83, I will explain the differences to you, but the emulator will follow the same pattern, okay? So the TI-84 will be the same option, so it's not that big a deal. Okay, so I have that handy. Okay, so today's lecture, we're definitely going to cover this concept of correlation, and we'll probably start regression a little bit during the second half of class, okay? And what this topic is this is section number 2 of our course, if you remember from the syllabus. And this is about looking at the relationship between 2 variables. Okay, so the relationship between 2 variables. So there's 2 main topics we're going to cover here. Okay, this concept of correlation, and then this concept of regression. Okay, what correlation looks to do is it looks to study or measure the strength of the relationship between 2 variables. So let me put that. Strength of relationship. And what regression is going to look, you'll see, is we're going to look to model the relationship. All right, in both of these cases, we're going to rely very, very heavily on our graphing calculator to do this. All right, so the first part of class today is concept of correlation. All right, so we're going to work with this example throughout class today. All right, so suppose your instructor is interested in seeing if the amount of time students spend studying for an exam can influence their grade, okay? All right, so first off, let's just think here, okay? Going back, sorry. All right, I'm looking at study time and a student's grade, okay? So I have 2 relationships here, okay? Study time and then the student's grade on, let's just say on their first exam. Do you all, and just in chat, think there's a relationship between these 2 variables? Yeah, I think so too. Yeah, to a certain degree, right? Like depends on the class and innate ability and things like that. But yeah, to a certain degree, how much time you spend studying has an influence on someone's grade. Okay, so let's just say last semester, all right, in a recent exam, in my statistics course, your instructor randomly samples 8 students. Okay, so the sample size here is 8, all right? And I observed the following. I have this one variable on hours of study and this other variable called exam score. All right, so look, I have 1, 2, 3, 4. I don't have a value for someone who studied for 5 hours. Okay, that's fine. 6, 7, 8, 9, and then exam scores. What relationship are you seeing here? Just by looking at the values, can anybody describe the relationship just in layman terms? Okay, direct relationship, that's fine, yep. Okay, positive, what do you mean by positive? Yeah, okay, there you go, right there in the form. This is just the basic relationship we're seeing. Okay, the more time you spend studying, the higher your grade. Okay, that's great. Okay, that's just the layman's terms of the relationship here. And some of you are hinting at some of the other words that we'll talk about in class today, like positive and correlation, things like that. So obviously, instead of us just saying, oh, yeah, there's a relationship here, the more time you spend studying, the higher your grade. What we want to do in class today is we want to put mathematical terminology to this. And then what we want to next do is put mathematical equations and concepts to this relationship. Okay, so we have two variables. The first thing we want to describe is or how we identify the variables. Okay, so we have two variables. Now, how do we classify them? Okay, so when you want to study the relationship between two variables, you have something called a response variable and something called an explanatory variable. All right, so just a real simple definition is the response variable is a variable whose value can be explained, right, by the value of the explanatory variable. Okay, so we have, I'm going to write it actually this way first. Explanatory variable. And then we have this thing called the response variable. So basically what's going on here is the explanatory variable explains the value of the response variable, okay? All right, so the explanatory variable predicts or tells or explains this response variable. So just out of curiosity, you have two variables here, hours of study and exam score. Which one do you think explains the other? What I'm asking is this, do you think your exam grade explains the hours of study or your hours of study explain the exam score? Anybody got a guess? Thanks, Pamela. Yeah, I agree. I agree. Both of those right there. What I think here is we're seeing that the hours of study is the explanatory variable, and what responds to your hours of study is your exam score. Okay, so next in mathematics, we have two variables. Generally, what two letters do we use when we have two variables in mathematics? Okay, one is X, absolutely, and what's another one? X and Y. Yeah, thank you. Thank you, everybody. The explanatory variable will always be our X variable. This will always be our independent variable. And our response variable will always be denoted with a Y, okay? And this will be our dependent variable. Okay, so what we're saying here is your exam score depends on how many hours of study you do. Okay. So one thing you should do, right? We have the first exam coming up is you should study, right? So that's the whole point of this example, silly example here is study for your first exam. Okay, what we want to do now is look at a visual representation of the data. And this visual representation is called a scatter diagram, but I will always call it actually a scatter plot. They're synonymous with each other. Okay, and it's just a graph that shows the relationship between these two quantitative variables measured on the same individual. So if we look back at our data set here, even though there's two variables, each of these variables correspond, to one person. So like for student 1, these are both his variables, his X and Y variables. Student 2, these are his or her two variables, and so on and so on. All right, so each individual in the data set is represented by a single point in the scatter diagram or scatter plot. And the way you do this is you set up the first quadrant of the Cartesian plane, and then you plot these like ordered pairs, okay? The explanatory variable is plotted on the horizontal axis. So X here, this would be the hours of study. The Y variable here, that gets plotted, the response variable gets plotted on the vertical axis. And what you do here is you plot them as XY points. Like here would be the first point, second point, whatever, so on and so on. The good news is we're going to show you how to, I'm going to show you how to have your graphing calculator do this for you, okay? So what you're going to see here is I want to create now, using our graphing calculator, this scatter plot for the data, okay? All right, so let's take our graphing calculator out, all right? And everybody, pause if you're writing notes, or please pay attention to these next steps, okay? Because what I want to do is I want us to, every single one of us, to reset our calculator so we're all starting from the same position on our calculator. So to reset my calculator, all right, I'm going to hit second function, and then you should see this memory button down here. So second function, memory, all right. And if I want to reset my calculator, what option is it there? Yeah, so you just want option number 7. So all you have to do is press 7 on your calculator. All right. It's going to ask you, what do you want to do? I want all RAM. I want to reset and clear everything out. So I want option number 1. So I'm going to press 1. Yep, start over. No problem, Dennis. Okay. So what you're going to do is you're going to hit second function and then the plus sign. Okay, for memory. So the second function, memory here. Is that good, Dennis? Okay. Then it's option number 7. And then it's option number 1. And then it's going to say, hey, are you sure you want to do this? And we're going to press 2 for yes, I want to reset this. So you should see something like this on your screen. Okay, if you have a TI-83, it's just a little different. Next, what we want to do, we want to take our data and I want to plug it into the graphing calculator. So I'm going to hit the stat button on my calculator. And if I want to input data, it's number 1, edit the list, okay? So I'm going to hit enter here. Now this is incredibly important. When you're going to plug this data into your graphing calculator, L1 always gets the explanatory variable, okay? So that's the hours of study. So we're going to 1, 2, 3, 4, 6, 7, 8, or 9 under L1. And then L2 always gets the response variable. So now we're going to start putting in those exam scores. 50, 54, 60, 65, 78, 82, 85, 82, 85, and then 88. All right. Everybody with me so far? Got the data plugged in? All right, good, thank you. Since we restarted, oh God, I can barely speak today. Since we restarted our calculator, what we have to do, reset our calculator. We have to turn back on our stat plot, okay? So again, I'm gonna press second function here, and I want this stat plot right here, second function stat plot. So you should see this on your screen. Everybody, if you reset your calculator, what you should see, it should say plot 1, ... off. Okay, so under number 1, I'm just going to hit enter. And notice how it's highlighted off, but it's blinking saying, hey, do you want to turn your plot on? We're going to go, yes, we do. So we're going to hit enter. Now it's on. And if you remember last week, we did the box plots here. This is a scatter plot right here, okay? The one that's already highlighted. So you do not have to do anything, okay?
Professor?
Yeah.
I'm sorry to interrupt you, but you kind of lost me after you entered the exam grades.
Yeah, no problem. I get it. So how I got here, right?
Yes.
Okay, no problem. No, it's okay. You can interrupt me anytime, all right? Gives me a chance to pause and have a sip of coffee, so interrupt anytime. What we have to do is we have to turn this stat plot on. So this blue button here, stat plot, you hit second function and then stat plot up here. So second function, then y equals. Are you with me here? How do you delete a number to go back? Leonardo, are you asking like under here? Is that what you're asking? All right, well, okay. To go back here, plot one, I'll get there in a second. Plot one, under plot one, you're going to hit enter. You're just going to turn it on, and that's it, okay? Turn your mic on and ask your question. I am having a hard time understanding what you're asking me.
So when we was plugging in the numbers,
yeah,
by accidentally put in L1 a 5. I'm trying to take out the 5.
Oh, no. Just go to the top of L1, hit clear, and then just re-input the data.
Professor, I have a question.
Yeah.
Are you able to do like a tutorial on how to do it and post it on Blackboard, or?
I'm going to record this lecture.
Okay.
If you want, I have some extra videos that I can post in Blackboard if you want me to.
Okay, thank you.
Yeah, just please shoot me an email and remind me. Okay.
Okay, thank you.
Yeah.
I also have a question about the calculator.
Sure.
So I was trying to do the whisker box plot thing the other day again.
Okay.
And I noticed that with the outliers, you know how you put that little star?
Yeah.
It wasn't appearing on the calculator. Do I have to like hit a specific like?
So let me show you. So let me just pause for a second. So the good thing about this class is I record the videos. So you can literally go back and pause and watch all this again. So that's a definite plus. For your outlier question, if you did the stat plot, like.
Mm-hmm. Yeah. I hit the box thing right there, but instead.
Hold on, you did this one, right?
Oh, okay.
Is that the question?
Yeah. All right.
And did you do that one and no outlier showed up?
I probably hit the one next to it.
But hold on, let me just say something. If you select this one right here, and like, let me just show you real quick. And you see something like this, that means there's no outlier. So you can have the outlier one selected, and if there is no outlier in the data set, it'll just give you a normal box plot.
Okay. So
there's no reason to actually even have to select this one. Okay, but anyways, back to the stat plot. Here, we want to have this one selected, okay? And don't worry, we're gonna do this examples like 3 times. I have like three or 4 examples we're gonna do, okay, over the next 2 weeks. So don't stress. We're gonna get a ton of practice in. Okay,
Sorry,
so
I have another question.
Yeah, go ahead.
So this part's not on the next test?
This is on the next test, yeah.
Oh, okay.
Yeah.
All right, thank you.
You're more than welcome. Okay, so we got this little stat plot here. This guy pressed. So now press zoom and then number 9, okay? And how many people on their graphing calculator see this? Is anybody else? A couple people do. All right. If you do not see this, okay, and you're getting some weird error in your calculator, what we will do is at the end of class, I'll stick around and I'll answer anybody's questions with their calculators, okay? All right, so don't stress too much. All right, but a good amount of people see this here.
Where's the zoom button?
You see right here?
Oh, okay. Okay, thank you.
Danielle, when it says error, when you press stat under number 1 edit, do you see L1 and L2 at the top? Okay, do you have the data perfectly lined up? Usually you'll get an error because you have one data missing or something. Yeah, okay, so there, that's why. Yep, and that's why. Yep, okay. So let's just go back and follow along on this for now, okay? All right, so looking at this. Now we want to put some mathematical terminology to this, okay? What do we see when you look at this scatter plot? So the scatter plot does describe the relationship. And when I say describe, what I mean by that is it helps explain the relationship between the two variables. And looking at this, it's not perfect. Okay, yep, but what L word does this kind of look like? It's not a perfect, starts with L, linear, thank you. Yeah, this looks like a linear relationship. And a lot of you were talking about this. It actually, because the line here that the relationship looks like it follows is sloping upward, it looks like a positive linear relationship. Okay, a positive linear relationship. So these scatter plots here, these scatter diagrams, scatter plots, no matter what they look like, they do explain or show the relationship, okay? So these all explain or show the relationship. The two that we will most likely or most work with this section is this type and this type, okay? When you do a scatter plot and it looks like it's sloping upward like this, it's explaining the relationship between the two variables. It's saying, hey, this is a linear relationship, okay? This looks like a positive, okay? This one here looks like it's sloping downward, okay? This also explains the relationship and it looks like a negative relationship, okay, with a downward slope. These next two types, we're not going to necessarily see in this course, but when you look at something like this, it looks like a parabola, okay? This does explain the relationship. It's just saying, hey, this is a non-linear relationship. This one here, like this kind of looks like, if any of you have taken an algebra class, it looks like a cubic. It's definitely explaining it. It looks like a non-linear relationship. And if you have a scatter plot that's just all over the place, I'm just going to even add a few more dots in here, okay? Just all over the place, the scatter plot does still explain the relationship between the two variables. It's just saying, hey, guess what? There is no relationship. Still explanatory. Okay? But for this class, what we're mostly going to focus on is this stuff right here, okay? This linear relationship between variables. Okay, so I've described or we've talked about things being positive or negative. So two variables that are linear related are positively associated, and this gets a little wordy, but I'll just kind of put it in layman terms. When above average values of one variable are associated with above average values of the other, and below average values of one variable are associated with below average values of the other variable. Okay, what does that mean? Really, it is two variables are positively associated if when one variable increases, the value of the other variable increases. So it's upward sloping. That's all it means, okay? And that's what you see here, upward sloping. A negative relationship, okay? Ignoring this above average stuff, if that seems weird, two variables are negatively associated when one variable increases, the value of the other variable decreases. Okay, like look here. As the explanatory variable increases, the value of the response variable goes down. Okay, so it's just a negative slope in the variables. all right? And this is what we're going to study, this positive association and negative association. Okay. What we want to do now, it's one thing to just say, hey, these variables are positively associated linearly, these variables are negatively linearly associated. What we want to do now is measure the strength of that relationship. So for example, let me give you an example here, okay? Looking back at this data set here, okay? I think there probably is a strong relationship between the hours of study and exam score, okay? How about instead of hours of study, I had put cups of coffee, okay? Obviously for me, there's a strong relationship, but do you think cups of coffee might be a good indicator of how well somebody scores on an exam? No, I mean, so here's the thing. There might be a relationship there, right? Coffee makes you more awake, maybe, okay? But it's probably not as strong as a relationship as how much time you spend studying. So instead of just saying, I don't think it's as strong, or, oh, it's a very strong relationship, we want to put a numerical measure to it, okay? And to do this, we use what's called, all right, the linear correlation coefficient, okay? That's all I'm going to call it for. Some other textbooks might call it the Pearson product moment correlation coefficient. That seems weird, but we're just going to use the linear correlation coefficient, okay? And what this does is it measures the strength and direction. Okay, so what I mean by direction is it tells me if it's a positive or if it tells me if it's a negative, okay, just by the value of it. All right, between two quantitative variables. All right, so there's two linear correlation coefficients. There's a population coefficient, which is given by the Greek letter rho, looks like a P, all right? This is a parameter, if you remember. All right, and then there's one that's we denote with just with the letter R, okay? This is a sample correlation coefficient, and this is just a statistic, okay? In this class, all we're going to do is look at the value of R, a sample correlation coefficient. We will never do a population linear correlation coefficient, so won't do in this class. All right, so let me give you the formula for how you calculate the linear strength of a relationship. And it's this formula right here. Okay, so the sample linear correlation coefficient R is given by this crazy formula. What does this symbol right here represent? This thing that looks like an E? What does that represent again? Yep, okay, so it's the sum of each X value minus its mean divided by its standard deviation times each Y value minus Y bar represents the sample mean of the Y variables divided by S sub Y, which is the standard deviation of the Y variables. You figure out what that sum is, and then you divide by N minus 1. All right. So here's my question for you. Does this formula look easy? Would you guys like to do this stuff by hand? No, I don't want to do this stuff by hand, okay? This formula here, all right, we're going to show you how to use your calculator for this. All right, so you're never going to have to do this linear correlation coefficient by hand. Okay, just know we're going to spend the rest of class looking at the value of R. That's more important. So for us, we just want to know the value. Okay, we just want to know the value of R. So we're going to have our calculator do us for that. Okay, so thank gosh that we're going to do that. But just know that this value R, there's an actual formula behind it. Okay, so before we talk about or show you how to use the calculator for this, let me give you the main properties of this value of R, this linear correlation coefficient R. The first is this formula. The linear correlation coefficient is always between -1 and 1 inclusive. Always, 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 okay? So it's like never a value of 2, okay? Or -2, all right? It's always between -1 and 1, all right? It can be 0, it can be -0.3, it can be -0.75, it can be 0.75, it's just always between -1 and 1. All right, if you have the value R, then this is what's called perfect positive linear correlation exists between the variables. And what you would see on your scatter plot is you would literally see the scatter plot as a perfect straight line like this, okay? So going back real quick, in our example, it's not a perfect straight line, it's off a little bit, okay? So we won't actually even do examples like this in class, okay, where it's like a perfect straight line, but that's what a value of +1 means. If you have R is equal to exactly -1, then there's perfect negative linear correlation. And what that looks like is a perfect straight line going downward like this. Again, we won't ever do exactly perfect negative linear relationship, okay, because that type of stuff generally doesn't exist in too many interesting real world examples. Okay, so the closer R is to +1, okay, like numbers like 0.9, 0.8, things like that, the stronger the evidence of positive association between the two variables. Similarly, if R is equal to -1, or closer to -1, stronger the evidence of negative association between the two variables. So going back real quick, I know I hinted at this already, but for our example here, do you think R will be close to +1 or close to -1? Close to positive or negative? Yeah, I agree. It should be really close to +1. So this is another important thing. If R is close to 0, there is little or no evidence exists of a, this is important, linear relationship. Okay, so if R is equal to 0, there can still be a relationship. It's just implying there is no linear relationship. All right, so the linear correlation coefficient is a unitless measure, okay? So the value or measure of X and Y play no role in the interpretation of this. So there's no units, just a number. Yeah. Technology. Let me show you real quickly what some graphs might look like for different values of R. All right, so here and here were those perfect positive relationship. You can see a like perfect straight line. Over here is perfect negative. You can see whoosh, perfect straight line going down this way. This is an example of something that has a linear correlation coefficient of +9, okay? Definitely you can look at the data and you can see the upward trend. It's not a perfect straight line, but you can see the upward trend. Same thing with -0.9. You can see the downward trend very, very clearly, okay? Here's something of 0.4, and here's another one of -0.4. You could still see the relationship. It's still going upward, just the data is a lot more spread out. Negative implies it's going downward. You can still see the downward trend, okay? But the further it gets away from 1, the more spread out the data is. And here are two R values close to 0, okay? Here there is no relationship, and here there's a non-linear relationship, okay? So even if you have a value close to 0, you can still see there is a relationship, it's just non-linear. Okay. All right, let's now calculate the R value for our example. Okay. And looking in the chat here, what you guys said here is it should be close to +1. Okay. So what I have here on the screen is how you see this on a TI-83, but I'm going to follow along on our TI-84 here. Okay. So everybody take out your trusty graphing calculator that never lets you down. Okay. Have that handy. All right. Yep, it's always there. Like when you need a ride to the airport or something, it never lets you down. No one found that joke funny? Okay. So you have to have the data plugged in. All right. So everybody make sure you have your L1 data here and your L2 data, and it's perfectly matched up. Okay. What we have to do next is we have to change a default setting in our calculator. Okay. So we have to turn on this setting called diagnostic on. Yeah, you'd be a rich person. Okay, in the forums there. Okay, so everybody pay real close attention and follow along here. I want to turn on this thing called diagnostic on. So there's this button called catalog down here. It's above the 0. So I'm going to hit second function, catalog. Okay, and you should see something like this on your screen. Okay, how many people are with me so far? Okay. Now you need to scroll down to the D's, but here's the thing, don't just scroll down to the D's, you'll be scrolling for a while. You see on your calculator, it has all these letters like A, B, C, D, E, F, G. You can see the letters of the alphabet there. If you press the X inverse button right here, it corresponds to the letter D. So press this button right here, and it should jump you right to the letter D's. So scroll down here. And we want this thing called diagnostic on. All right. All you're going to do now is hit enter. You should see diagnostic on, and then just hit enter again, and it should say done. All right. This is incredibly important. Did anybody not follow me what I did and needs to see me do this again?
Can you repeat the process? I kind of got lost at catalog.
No problem. So you go second function catalog. You see this little button here that says X with a -1?
Yes.
Press that. Now scroll down. Do you see this option called diagnostic on?
I'm not.
It's in your calculator. If you have a TI-83 or TI-84, it's there.
I got it. TI-83.
Yep, it should be there.
Okay. Probably pressed the wrong.
You see it or no?
No.
Okay, let me. All right, does everybody see my TI-83 emulator now?
Yeah, I see it.
Okay, so you're gonna go second function, catalog.
Second function.
You're gonna press the X inverse button right here.
Yeah.
And then you're gonna scroll down till you see diagnostic on.
Yeah.
Hit enter. You should see this.
Mm-hmm.
Hit enter. Over here, diagnostic on, hit enter. And everybody should see this. That says diagnostic on, done. Diagnostic on, done.
Yeah.
All right, anybody else still not with me?
Professor, on my calculator it says diagnostic off.
You gotta scroll one more till you see diagnostic on.
Yeah, but by mistake I already clicked that. So how do I go back?
So again, second function catalog, X inverse, diagnostic on.
Got it, thank you.
Got it? Everybody good? Anybody else not good? Yay, nay, forever hold your peace. Okay, next, you're gonna press the stat button on your calculator. So stat, over here I'll press stat. You're gonna scroll over till you hit calc. So calc, over to calc. The option we are gonna use this week, okay, is option number 4. It's called linreg. So option number 4, linreg, okay? So everybody hit enter. If you have a TI-83, it just says linreg and then AX plus B. Just hit enter again. Oh, I don't have anything plugged in here, that's why. But just hit enter again when you get there. Okay, over here you're gonna scroll down to calculate, hit enter, and everybody should see this on their screen. How many people see this on their screen? Okay. All right, perfect. We're gonna go over the next week, we're gonna talk about what A and B represent. R squared, we're not gonna talk too much about. R squared is called the coefficient of determination. And let me just go back here. Let me just quickly explain what the coefficient of determination is. Coefficient of determination, R squared, you'll study a lot more in your advanced methods courses, especially if you go to graduate school. It's explain the percent variation in the response variable that's explained by the variation in the explanatory variable. What that means, R squared has a value of 0.988, let's just say 0.99. So as a percentage, that's 99%. To go from an exam score of 50 to 54, you saw your explanatory variable change by 1. It means 99% of that 4 grade difference is explained by the 1 additional hour of study, okay? But for now, what we're really just interested in is R. Okay, so we said R should be close to +1. Is this value really close to +1? We got 0.9943. We'll go 4 decimal places. Yeah, that's super close to +1. And that's how we do this in our graphing calculator, okay? So I know we messed around with a lot of settings, but is it not too bad? Okay, we're gonna get a chance to do this again, all right? Let me just see something here. How many slides do we have left? Yeah, let me just get through this example here, okay? We're gonna skip our break a little bit just because we spent a lot of time on the calculator. So let me finish these slides and we'll see how far we get. Okay, I only have 7 left or so. Okay, so here's another example, all right, that we're gonna do in our calculator, all right? So I have this set of data here, okay? We have our first variable, variable 1, and we have our second variable, variable 2, okay? We're just gonna assume that variable 1 is our explanatory. So our X variable and variable 2 is our response variable, our variable y, okay? So let's look at the scatter plot, describe the relationship, and calculate r, okay? So everybody grab their trusty calculator again. So what we're gonna do is we're gonna go into stat, and we're gonna have to input this data. So everybody go to number 1, and you have to clear this data out, okay? So go to the top here, hit clear, never hit delete. Go to the top here, hit clear, and hit enter. All right, now let's start the process of putting all these in. Okay, so under L1 is 29.8. And then as I'm putting this data in, you put it in as well. All right, so I put in all the variable 1 into L1. Now variable 2 I said is our response. I'm going to put under L2. Uh, 327, 456, 509, 497. Sorry, this takes a little bit. 596. 573, 661, 741, 809. You guys probably were able to do it faster than I was. All right, how many people have their data plugged into their calculator so far? Okay. All right, good. I'm getting older, so everything takes me a little bit longer. Okay. So let's look at the scatter plot. Thank you for the pity laugh. I appreciate that. All right. Having a newborn and I'm almost out of coffee, everything is just harder these days. Okay, yeah. You notice I didn't turn my video on because I am completely disheveled today. All right, so you're gonna have another laugh. All right, hopefully you guys find this humor a little funny every once in a while. So here's the problem. Our graphing calculator is zoomed into the previous example. So everybody on their graphing calculator press zoom. And we want zoom stat number 9 again, okay? And you should see something that looks like this. All right, how many people got this exact graph on their calculator? Okay. All right, so I'm going to go back here. Marcos, did you were you able to get the same scatter plot that we had before? So after you plug in the data, if you turned on your stat plot, just hit zoom, and then you want zoom stat. Okay. All right, so look at everyone. Just pay attention to this. Like, look at the trend here. We got the scatter plot. Great. How would you guys describe the relationship between the variables? Using some of the terminology. Does it look like a positive or negative relationship? Yeah, looks positive. Sure. Does it look somewhat linear? Does it look like there's still a straight line pattern here? Not perfect, but yeah, somewhat. Yeah. So I would say there's a positive linear relationship. Like as the x variable increases, so does the y. Yeah. So it looks like there's a positive linear. Okay. Next, let's measure the strength of this. Okay. What do you mean you don't know how to put in scatter plot? I don't understand your question.
Like, how do you change it from a regular graph into the scatter plot?
Okay, so hit on your calculator, hit second function stat plot up here. Does your calculator say plot 1 on? Okay, so hit enter. And where it says on, hit enter again. Okay, so now it should say on. And is this graph plotted? Do you see this one here? Is that one selected, Marcos? Okay. Now just hit zoom and zoom stat. Do you see this? Yay, nay? Okay, good. There you go. That's why. All right, so the next thing said, let's calculate the value of R. Just real quick in the chat, do you think it should be close to positive or -1? All right, yeah, I think so too. Let's check. So to find R, you're gonna hit stat. You're gonna go over to calc. And again, you want option number 4. So you're gonna scroll down to option number 4. And you're gonna hit enter. Now, if you have a TI-83, just hit enter again. With the TI-84, let's scroll down to calculate. And you should see something like this, okay? How many people see this on their screen? Awesome, okay. So the bottom values are, so it looks like 0.9471 when you round it, okay? Okay, but let me now tell you what the 2 variables are, okay? Variable 1, what you look here is I add a column here with year, and it just looks like this is what you're seeing. As time has gone on, this is a data set from the year 2000 to 2009. Variable 1 has increased, and for whatever reason, variable 2 has also increased over time. Variable 1 here is per capita cheese consumption. Okay, so basically this is how many pounds per year of cheese the average American consumes. Okay, so like in 2000 it was 29.8 pounds per year, and then by 2009 it had gone up to 32.8 pounds per year for whatever reason. Variable number 2 is the number of deaths by being tangled in bed sheets. Okay, usually I get a chuckle or two out of this, but it's actually a pretty sad thing. It's usually like infants who get tangled in bed sheets, so it's very sad. But so for whatever reason, the number of deaths by bed sheets has gone up. So what's going on here? Do you think these variables are really related? Yeah, I don't think so. No way. Okay, per capita cheese consumption is not explaining why death by bed sheets is going up. It's not. It's just not. So you might have heard this expression before, correlation does not imply causation. Okay, so just because 2 variables are highly correlated does not necessarily mean, yeah, you heard it in psychology. Yeah, it does not necessarily mean there's actually a real relationship going on here, okay? So you can just see over time, here's the example, just for whatever reason over time, they're just going up together. So generally what this is, the reason for this, okay, so another way the 2 variables can be related even though there is not a causal relationship is through what's called a lurking variable. So a lurking variable is a variable that's related to both the explanatory and response variable. So it's just some external variable that's actually impacting both of these variables that's causing them to go up over time. I actually don't even know what's causing the lurking variable here is. I don't know what's causing these 2 variables to go up over time. But let me show you a good example of a lurking variable. It turns out that if you were to just look at, this is kind of funny, ice cream sales and crime rates over time, okay, in a given year, they have a high correlation, okay? So does that mean that local government should shut down all ice cream shops? No. Like what's causing ice cream sales to go up and crime rate sales to go up is the temperature. All right, as temperature rises, people go out and have more ice cream. As temperature rise, crime rates generally go up. Okay, so that's an example. So you might say, oh my gosh, ice cream sales are causing crime rates. Let's shut down all the ice cream shops, which would make me very, very sad. That's not really what's going on here. This other variable is lurking in this behind the scenes and impacting it. All right, does that make sense? Okay, last thing I want to talk about, then we'll take a quick break, is how you actually know there's a linear relationship for sure. Okay, so like all these values, all the examples I did, like we're just going to go back to this one here. Okay, we're going to look at our first example here. The R value here was close to 1. So for sure there was a linear relationship, a positive linear relationship. But what if it was 0.6, 0.5, 0.4? Like what's the cutoff for saying, okay, the value is not high enough to say that there's a linear relationship? Well, it turns out there's this test you can do, all right? And it's using these things called critical values. So the first thing you do is you look at the absolute value of your correlation coefficient. Okay, so R was 0.9943. The absolute value of that is still 0.9943. Just if it was negative, you just make it positive. The second thing you do is you find the critical value in the table from our textbook. I have the link here. I have another table on the next slide, and I'll show you how to do that. And then all you do is if the absolute value of this correlation coefficient is greater than the critical value, we say there's a linear relationship. Otherwise, there's not. All right, let me show you exactly what's going on here. Okay. So this is the table of critical values here. This is the one from our textbook. Okay, I prefer this one right here. It's just nicer. Okay, it's just cleaner looking. So basically what you do is you go back to our original problem, okay? So all the way back to the first slide. Sorry, I know I'm going fast. All right, and you count how many students there were. Our sample size was 8, okay? So you go to the chart and you find 8, okay? The reason I like this chart is because it just lists n. Here you have to do this n minus 2. So 8 minus 2 would be 6. It's just a little different. This is why I think this one's easier. And then this is its critical value. You see it's the same one, but I hope you guys agree that this chart's a little bit easier to use. And basically what you do is you say, is the R value greater than this? So our R value was 0.9943. Yep, yes you will. Even if you're not explicitly given, you can just count the number of data values, okay? And do you see how our R value is greater than that? Sorry that my chicken scratch there was bad. But because it was, we can say for sure, yes, there is a linear relationship. So if we had done this problem with 8 students and the R value came back as like 0.5, excuse me, we would say, hey, there's not enough evidence to say there's a linear relationship. And I have it a little bit cleaner here on this next slide. You look at your R, you look at this value here, and as long as that R value here is greater than the corresponding number on the chart, okay, you can say, yes, we have strong evidence that there is a positive relationship between the variables. All right. And don't worry, we're going to get to do this chart stuff again, okay? But this was just a quick introduction to it. All right, what do we think? Do we have a okay understanding of the linear correlation coefficient? Okay. So right now it is 2:08. Let's just take a 5-minute break. All right. We'll start back up at 2:13 exactly. So you got 4 minutes and 42 seconds, 48 seconds, 47 seconds now. And then we'll start up with the next slide. Okay, so I'll be back at 2:13. No, to answer your question, so the exam will be on everything we cover up to on Thursday. Okay, so it's going to cover correlation that we talked about today, and then I'm going to start regression today, and then I'll finish up regression on Thursday, and it'll be on everything that's on your first homework and your second homework. Does that answer your question? Okay, yeah. That's okay. Yeah, I'll answer your question and then I'll get back to class. All right, so if you look back, first off, don't stress about the first exam. I know that's easier for me to say. I don't have to actually take the exam. But if you look at our course schedule, the first exam tends to be the easiest exam. So every other exam that we have, I have a whole class built in that does a review day beforehand. So what we'll do on review days is I'll literally say, okay, everybody, let's do a practice exam together for our class, okay? What's gonna happen on Thursday? Thursday, I'm going to lecture for probably the first hour and 20 minutes to cover the rest of regression because I'm not gonna get through all of it today. And then I'll spend the last half an hour doing a quick review for you of the main topics for your exam, okay? But I promise you this, there are 0 surprises on the exam, okay? If you look back in the classroom and you look at the 2 homeworks that I gave you, okay? And then also, sorry, to go back here. And if you look at this sample exam, you can see the type of questions I'm likely to ask, okay? And you'll notice that there's all the same type of stuff like calculate the range, standard deviation, the quartiles, test for outliers. This is a regression question. Cover that next time. But like you can see, hey, there's a scatter plot here. What values of R are these closest to? We just did that in class. Classified variables, that's homework number 1. It's very, very straightforward stuff, okay? If you spend a lot of time on this homework number 2 and really give it a good shot, it's gonna be real hard not to do well on the first exam, okay? Does that answer your question? Any other questions before I get back to it? You guys will do great. I get good vibes. Okay, so with the time we have left, what I want to do is I just want to start, because we have about half an hour left. I just want to get started on this regression stuff, okay? And now what regression is now what we want to do is we want to model the relationship. Okay, and what I mean by that is we want to put a mathematical equation okay, to the relationship. All right, so the first few slides are just a review of what we did. They're the exact same thing, so I'm going to skip those. And so what's next? What's this concept of regression? Okay, so since we know there is a linear relationship between the 2 variables, okay? So going back, I shouldn't have skipped so far ahead, but I want to go back and I want to look at this first example we started class with today, okay? So we said hours of study was our explanatory variable X, and our exam grades was our response variable Y. All right, so this was our scatter plot for it, okay? So over here we had hours of study. Here we had exam scores, which is our Y variable. And now what I want to do is I want to put a mathematical equation to this, okay? And because it's a linear relationship, the mathematical equation we will use is we'll use the mathematical equation for a line. So this is our mathematical equation for just a straight line. Okay, x here, this is our independent variable. Okay, in this case here, it's our hours of study. Y here, okay, this is our dependent variable. Okay, in this case, it's the exam scores. What does the letter M represent for the equation of a line? Does anybody remember? Yep, thank you. It's the slope. Okay, and just remember in mathematics, what a slope represents is it represents a rate of change. Okay, that's what a slope is. It's the rate of change. And what does B represent for the equation of a line? If M is the slope, anybody remember what B represents? Starts with an I. Thank you. Yeah, it's the y-intercept. Okay. So now here's the thing. Look at that line right there that I put there. Does that line do a good job going through the data? What do you guys think? Like, do you think that kind of? I think it's not bad. It's not bad. Okay. So what our goal is, what we want to do is we want to find the equation of this line. Okay, that's our goal here. We want to find the equation of this line. All right, and why do we want to do this? Okay, so we want to model our relationship so that we can estimate unknown values. Okay, so if you remember, looking back at our chart here, okay, if you notice I had hours of study 1, 2, 3, 4. Do you notice how I'm missing 5 here? All right, suppose I want to know, hey, I only have 5 hours to study. All right, what would my exam score be? Well, it would be somewhere between a 65 and a 78 probably, but what exactly would it be? Or what if I was like, okay, I got a ton of time this week, I want to study for 10 hours. What would I expect my exam score to be? All right, this is what we want to use the model for. So this model, so the mathematical equation. Okay, that's what we're going to use this for. All right, so what we're actually looking for is we're actually looking for the line that does what's called, quote unquote, best fits the data. All right, so we want to find what's called the best fit line. Okay, the best fit line. So now if you look here, here's the first quadrant of the Cartesian plane. There's an infinite number of lines, literally an infinite number of lines you could pick from, okay? Like this line here that I just put up on the screen, okay? Does this do a good job of modeling the data, going through the data? Does it do a good job or bad job? Terrible, right? Terrible. Okay, how about that line, this vertical line that I just drew? Does that do a good job modeling the data? Nope, nope. All right, how about that one? Nope, nope. That one doesn't either, okay? So how do I know that this is the best fit line, okay? All right, so we can find this quote unquote best fit line using what's called least squares regression, okay? So this is, you're gonna hear me call it the LSR line, the least squares regression line. All right, so how do we, or for example, what is least squares regression? And so here's the concept, a basic concept. here are all our data values. Do you notice how that they don't follow like a perfect straight line? There's literally no way I can draw a straight line through all of these, okay? I just as a pause for a second, do you guys hear my my young son crying in the background? I'm just curious. No, you don't hear him? Okay. All right, good. You know, my mother-in-law comes over and helps us on Tuesdays. So you don't have to worry. It just always distracts me. You know, I don't know how many of you have children, but as soon as you hear your child crying, you're like, oh no, I gotta go help them. Except at 2 in the morning when they start crying, I'm not too happy about that. But anyways, ignore that. Let's go back. Okay, so how do I find this least squares regression line? So notice how like the line that goes through the data, you can't draw a straight line through all the data, but do you notice how it misses some of the data points here, this least squares regression line? Like it doesn't perfectly go through it. Like let's take this one right here. Okay. This is the X value 6. The actual value of 6, somebody who studies for 6 hours, let me go back. Somebody who studies for 6 hours gets a 78. Okay. But this line, which models the data, says the following. If a person studies for 6 hours, the line says they should be getting this number right here. And let's just say that's a 76. Okay. Did the model get it right or wrong? Okay, did you notice how the model underestimated what somebody would get? Okay, right here, the model was off a little. Okay, or another way of saying this is the model made an error. And that's okay, model's gonna make an error, it's not a big deal. So what the least squares regression line does is it's the line that minimizes the sum of the squared errors. Okay, the reason we square it is sometimes you make a positive error, sometimes you make a negative error. So you want to square them to make it all positive. And so this line minimizes the sum of the squared vertical distance between the observed values of y. So this 78 here, this is the observed value. Okay, the actual value. And what we call those of the predicted, okay, by the line that we denote with this notation here. It's y, it got cut off a little bit, y hat, okay? It looks like the y value with this little cap on top of it. It's literally just called y hat. Whenever you see this in statistics, it just means estimated or predicted. So this equation here, this red line here is going to be my y hat equation. Okay, so this mx plus b. Okay. So looking at it here, an error, which is sometimes going to be referred to as a residual, if you look at that one point I was talking about here, okay, this was x is equal to 6. The y observed, the y actual value, okay, the student actually got a 78, but the line, the model said, let's just say, I don't know what exactly it would be, but let's just say the model said the student got a 76. So the error there was a 2, okay? Every single one of these lines has an error. So all the least squares regression line does is it minimizes the sum of the errors, okay? So just, if you're only going to remember one thing, least squares regression minimizes the errors. Okay, it's the line that makes the least amount of errors in a data set. Does that make a little bit of sense? Yay, nay? Sure. That's a good response. All right, so let me give you another another visual, okay? Just a different example, okay? And then then you'll see a little bit better how this works, okay? Suppose you have another data set, okay? This is just a different data set. And I know you can barely see it, but here are the real values of the data set, okay? All right, here, 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 and here, okay? This is the line that we say best fits the data. If you look at this point here, this is the actual data value, okay? And the actual value is 5.2. But my model is saying, hey, when you give me that X value, I'm saying the person should have got a 4.75. Well, the difference of that is 0.45. So the model was off, okay? The model was off, all right? Like going back to this example here, okay? Hey, I studied for 6 hours, I scored a 78, but the model says I should have scored a 76. Okay, the model was off. Model just made a little bit of an error. That's it, no big deal, okay? All the least squares regression line does is it takes all the errors your model would make, sum them up, and it's the line that makes the smallest amount of errors, okay? Does that do a little bit better? Okay. So how do we find this line? Okay, how do we find this least squares regression line? Okay, so our equation was this, was y hat. We're gonna do a bunch of more examples of this, I promise you. I think what might be best is we'll move on to like a legit actual example, and then we'll calculate an error and a residual for all of that. Does that sound okay? Instead of getting, all right, yeah, thank you. Okay, so for all our examples here, we're gonna be looking for this equation. It's gonna be y hat, so our estimated y value times some slope, okay, plus the x value, okay, which is our explanatory variable, plus some intercept. So there's 3 ways you can do this. You can do this by hand. That's what we're gonna do today real quick. Okay, and then what I'm gonna show you after we learn it by hand is I'm gonna show you how to do it with the calculator. All right. If we have time next class, I'll show you how to use Microsoft Excel for this, but I don't know if we will actually have time. So first off, I'm gonna put some formulas up here, all right? And do not get scared by them, okay? They're actually pretty straightforward. And then I'm gonna show you how to use the calculator eventually, okay? Okay, so how do you find the least squares regression line, okay? This is the notation the textbook uses down here. So it's y hat is equal to slope times x plus intercept. They just call the slope b1 and the intercept b0, okay? When you want to find this equation by hand, okay, you find the slope first. Okay, so you find b1 first, okay? And it's just a very simple multiplication and division problem. Does anybody remember from the first part of class what R stands for when you have 2 variables? It's the linear correlation coefficient. So it was this thing. Let me go back. It was this thing in our calculator. Yeah, thank you. The linear correlation coefficient right there. Okay. Does anybody remember in statistics what the letter S stands for? So S stood for the sample standard deviation. Do you notice how we have S with the subscripted Y and S with the subscripted X? Well, we had two columns of data, right? We had our explanatory variable and we had our response variable. So it's the standard deviation of the Y variables divided by the standard deviation of the X variables, okay? So it's the linear correlation coefficient times S sub Y divided by S sub X. After you find the slope, then you find intercept. Okay. Intercept looks weird. It's Y bar minus, this is why we find the slope times X bar. Okay. Does anybody remember what X bar stood for?
Sample mean.
Mm-hmm. But now I'm going to be more specific. This is the sample mean whenever you see the X under it of X variable. What do you think Y bar means then? It's the sample mean of the Y variable. Okay. So you need, I'm going to go through this again real quick. X bar is the sample mean and S sub X is the sample mean of the explanatory variable X. And Y bar and S sub Y is the sample, Y bar is the sample mean and S sub Y is the sample standard deviation of the Y variable. Okay. So here's what we're going to do. All right, and this is, we're going to end class with this, okay, because we got 15 minutes left. We're going to do the way we started class, okay? So if you remember, gosh, an hour and a half ago, we started class with this. We said this example, hours of study. This was our explanatory variable. Our variable X and exam score was Y, our response variable. We want to find this least squares regression line, which is given by this formula. Y hat is equal to B1X plus B0. To do this by hand, you need 5 things. Okay? You need the value of R. Can anybody look back in their notes and tell me what the linear correlation coefficient was for our first example? I think it was 0.9943. Anybody else agree with that? Okay, I'll leave the chat. I'll just assume in the chat that yes, we do agree with that. Okay, that was the first example we did. Okay, so we need to know the average of the X values, the standard deviation of the X values, the average of the Y values, and the standard deviation of the Y values. Grab your trusty calculator here, okay? Here's what we're gonna do. We're gonna go back into our calculator, we're gonna press stat, and we're gonna re-plug in this example. So go to the top of your list and clear everything out, okay? And you're gonna re-put in under L1, the X variables. Like so. And under L2, you're gonna put the Y variables, the exam scores, okay? So 50, 54, 60, 65, 78, 82, 85, and 88. What you're going to do next is you're going to have your calculator do all of this for you. The average of the X, the standard deviation of the X, the average of the Y, and the standard deviation of the Y. All right, and if you're struggling to like keep up with your calculator with just the limited time we have, just watch me do this, okay? So you're going to hit stat, you're going to go over to calc, and you want 2 dash var stats because we have 2 variables. Okay, so I'm going to go down to number 2. We're going to hit enter. We're going to go down to calculate. And anybody following along with me, did you get these values right here if you did this with me? I'm just curious if anybody kept up. Okay. I mean, like the good news here is look at this. X bar, the average of the x's is 5. S sub x, check this out. 2.99 or 2.9277, right there. If you scroll down a little, it tells you what y bar is. Y bar, 70.25. S sub y is 14.820. I'll round it to 4. Okay? So your calculator tells you these 5 things. So I'm just going to write these down, okay? X bar, the average amount that students spent studying was 5. The standard deviation out to 4 decimal places was this. Y bar was 70.25. And the standard deviation of exam scores was this. You find the slope first. I'll always specify it. But yeah, you can go to 4 decimal places. So it's R times S sub Y over S sub X. This is just a very simple plug and chug, okay? This is 0.9943 times S sub Y, which I have down here, which is 14.8204, divided by S sub X, which I have right here, 2.9277. Just for time, I'm going to quickly do this for us in my head. Carry the 1. This ends up being 5.0333. You do the slope. Next, you find the intercept. And you just follow the equation. It's y bar minus b1 times x bar. Well, y bar was 70.25 minus the slope times x bar, which was 5. And if you plug this in your calculator, you'll get 45.0835. So what that means is my regression equation, y hat is equal to my slope times x plus the intercept. Just so we're clear what this regression equation is, y hat, we're estimating the y value. So y hat is my estimated or predicted exam score is equal to 5.0333. What does x represent again? Yeah, so 5.0033 times the hours of study plus this intercept. All right, so let's just verify. I don't know. Let's just verify that this equation that I have actually fits the data well. Okay? So grab your trusty calculator again, okay? If you go back, you should, if you followed along, you should have the data plugged in your calculator. So I'm gonna hit zoom number 9. Okay, this is what the scatter plot looked like. What I wanna do now is plug this equation of this line into this and verify that it fits the data well. So I'm gonna next hit my y equals button, okay? And what I'm going to do is I'm going to plug this equation in. All right, so it's the slope, y1 is equal to 5.0333. To put x in, do you see this little button right here? It has x comma t comma theta comma n right here. This is the variable button. You're going to press this button, and then you're going to add 45.0835. You're gonna hit enter. And now all you're gonna do on your graphing calculator is hit this graph button. How many people were able to quickly follow along with that and see this? Does anybody see this on their graph calculator? Okay, if you don't worry, we're gonna get a lot of practice with our calculator. So look, we just found the line that best fits the data, okay? But I have some good news. We're gonna do, next class, we're just gonna do a ton more examples of this. But was doing it by hand, did it honestly seem like not fun? Okay, and I went through it really quickly. Like terrible, I never wanna do that again. You can be honest. Yeah, I agree. Okay, I don't either want to do it again either. The good news is you're like, never again. The good news is your graphing calculator will do this for you. All right, so hit the stat button on your calculator. All right, if you have this followed along. Go over to calc. And if you remember to find the linear correlation coefficient, I said it was option number 4. It was linreg. Okay, go down to number 4, press enter. Go down to calculate. And look here. It's saying, hey, look, y is equal to ax plus b. So they just called the slope a. Look what they got, 5.033333. Look what we got, 5.0333. Plus b, the intercept. We got 45.0835. The reason ours is a little different here is because we rounded values to 4 decimal places. Your calculator doesn't, but you have it right there. Was it just so much easier on the calculator? What do you guys think? Yes, everyone's just like, Matt, why don't you just show me this first? Okay. It's important to know how to do this stuff by hand, obviously, but like going forward, we will just use the graphing calculator. Okay, so what we're going to do next class, okay, I agree, so much easier. If you just look ahead in the notes, we're going to just do a ton more examples of this, okay, just a ton more. I've got 2 more examples, a bunch of questions on each, and what you'll be able to do is you'll be able to answer these questions. These will be exactly what exam questions are, and you'll be fine going forward. Okay. So I know class was a little quick today, but we'll pick up here on Thursday. I'll stop the recording and then I'll see if anybody has any final questions.